I'm Brian Wendell.
And I'm Joyce Farrell.
And we're here to describe to you the Image Systems Engineering Toolbox that we've been working on for a number of years. So the Image Systems Engineering Toolbox, which we refer to as ISET, is an open source MATLAB toolbox that we use a lot at Stanford for teaching.
Right.
And we also use in our consulting.
Right.
And the toolbox helps people visualize and quantify. It's really important to us with physical units, things like the scene spectral radiance, the field of view, the luminance level, and so forth, or how it is the optics turns the scene spectral radiance into the spectral irradiance, how we model the sensors, and how the sensors capture light and turn them into voltages and various sources of noise and imperfections in the sensor. And we model the image processing pipeline, and we also model the display itself, the display properties and display spectral radiance.
Right. And originally we developed this for modeling digital cameras when we did a lot of consulting for companies that were designing imaging sensors for camera phones. So that's we're going to talk a bit about the history of how we came to build this toolbox, and then talk a bit about how we hope to see it being used in the future.
Yeah.
Right. So we really don't know any of these people in this picture. They just represent.
This is nice, though.
Yeah, they represent the kind of teams that we would often meet with at different companies, and there were a lot of companies.
Actually, they kind of look like the students that we've taught at Stanford. We've been teaching this class for 15 years.
That's true, but they also look like the young engineers at these companies.
Yeah, they look like the students just after they graduate.
Right. And all of a sudden they're given the job of, you have to design an imaging sensor for a camera phone.
They're wearing nicer clothes than our students do,
Yeah, back in 2000, I think.
Yeah, that sounds right. So, and in fact, the students in our class, just like the engineers that we meet in industry, all come with a diverse set of skills, different kinds of expertise. Right. And there's a lot of stuff that they know really well and stuff that they don't know very well.
Yeah, so there'll be people in this room who are experts in optics, and some people who are experts in sensors, CMOS sensors, or FPGAs, and then image processing.
And that's because the parts that go into building a camera are actually diverse themselves. So this shows you the optics and the sensor and the electronics, and there's even mechanical engineers in there for stability, and there's just lots and lots of different
displays,
parts.
Right.
Yeah, the display that appears on either on the camera or subsequently for display. So you need people with expertise in these many different things, and they need to be able to communicate with one another. And the one language that it seems all engineers do speak at some point, varying degrees of fluency, is really software.
Right.
And so if you want to help people communicate with one another, it's really nice to have an integrated code base that people with these different types of expertise can come together and see what the impact of their particular bit, say the optics or maybe the sensor, if you make a design change, what impact does it have on
Right, and anytime you're designing a product, there's a whole history of other products that have benefited from simulation. So we wanted to put together a software environment that would simulate the entire image systems, so that people could see what would happen if you change different parts of that system. How would that impact the final image quality?
Right. And so again, they start with different languages, ray tracing and circuit design and math, but we boil it down into a common language, a common computer language that everybody can share and interact with. And the reason why it's so important to come together is because there's one product that's going to ship, and it's got costs and benefits, and the impacts of design changes need to be understood and evaluated before you commit.
Yeah, and there could be an engineer who worked really, really hard on some new image processing pipeline, and if it doesn't make a difference in the image quality, it's not going to get in the product.
Right. So you want to know that as soon as you can in simulation, prior to the construction of the full prototype, is an important way to get ahead of the curve. The other really important thing, we've said this already, but I don't think we can emphasize it enough, is that some people use in each of their own separate expertise. The people who work on optics have their own metrics, and people who work on sensors have their metrics, and they'll even overload the same word. They'll use a word like pixel or bit to refer to completely different things when they're describing different parts. So 14-bit camera means that each pixel responds over a range of 14 bits, but a 24-bit display means that each of the color components of the pixel has 8 bits, and then they add them up.
Yeah, so that's very confusing if you're using the same words to mean different things.
Yeah, so the software environment really helps clarify this, and particularly when you have a strong discipline in your software to try to stay in real physical units throughout the process, that really helps the simulation and helps the groups communicate. The reason I would say that we were often involved in product evaluations and that we played a role is because both Joyce and I have worked on vision science from the days that we were graduate students. And that's a field that's super important in certain areas of consumer photography. It's really the final arbiter of whether the device is any good or not.
Because these products are designing for people to look at.
And that's a field, the ability to predict what's going to look good, where you're going to see artifacts and so forth, that is not broadly trained in engineering. So the ability to integrate what's known from vision science into this normal engineering flow has really added value. We're seeing this again. There's a new development now in image systems engineering, new developments now in image systems engineering, because so many images are being used for machine vision applications and for learning, machine learning and convolutional neural nets. Imaging has been a really important part of that. And again, in that case, one would expect that the nature of the image itself would matter. A lousy image, well, you could do less well, and a better image, you could do more things. And we need some way to work with our colleagues who are experts in convolutional neural nets and machine learning to design imaging systems that help their algorithms perform.
This gets into how we see ISET being used in the future, which is to generate images that people who are working in this field can use for training.
Yeah, because when it's a simulation environment, you can generate huge amounts of data. And we have many colleagues who basically try to collect data by driving around in a car or downloading from Flickr, where there are all kinds of different cameras and uncontrolled, no ground truth and so forth. The simulation environment can really help improve that situation.
Right. And so what you're going to hear about in the beginning is really sort of the basics of ISET, which will seem applicable for digital cameras, but we really do see this as something that's evolving that's nice that we get to work on this over the years, and we get to adapt it to the technology that's being developed. So
so help keep us young, work on computer vision applications in the class. So just to summarize, we really think that the value of this software is to enhance collaboration across between people with different expertise, and to help them have a common language. It's a mix of language of physics with all the physical units that we've embedded, and software, which everybody coming through the engineering school has to learn to program at this point. The software helps you predict effects that component changes will have on system performance.
Right, so there'll be engineers that are working on different parts, somebody who's working on the optics, somebody on the image processing, and they can all work together in the same simulation environment, modeling their component and seeing what is the effect that their changes will have on the final image quality. Or in the case of autonomous vehicles, on the ability to classify objects.
And the final thing that we're really finding fascinating, and it's a new development for us, is with the growth of virtual reality and augmented reality systems. There's a lot of interest in designing camera systems, not just individual cameras, but arrays of cameras that are configured in different ways to go and acquire new kinds of information that you really that when we started in this business, we had just a single snapshot seemed pretty good, and then
now
video
it's surround
seemed pretty
video.
exciting.
Now it's all surround video.
It's a different world.
All different kinds of imaging systems.
And those are complicated systems, and modeling how you build them before you build them is really important. And we find that it's really helping people rethink things that they might try before you build them. Just go do a lot of software experiments and think about how you'd arrange it, and build those worlds before build the software worlds, the simulation worlds before you build the prototypes. So it's an exciting time, and we hope that you'll enjoy using this set of software tools.
And think of other different applications. So, for example, we're also using it for underwater imaging, and we've proposed a lot of different class projects.
We had all that fun with that guy in outer space who was saving the world from asteroids.
Yes, there's a lot of different things you can do with the simulation, so we hope you have fun with it.
Yeah, we hope you have fun.